Thank you very much for the organizer for inviting me to be here. It's a nice place to be. It's the Yossi sessions because there's Yossi and Yossi. I will start a little bit before I will talk about the superconducting issue. I want to talk about the CISS effect because I know that some of you know about it, but I want to give an introduction to what we see in the superconductivity. So first of all, I am from the Hebrew University. The Hebrew University is the oldest university in Israel. Those of you who haven't been in Jerusalem, it's quite nice. I don't know if you see the dots, but you have everything mixed together, all the major religions. So this is a Western Wall. This is one of the holiest mosques. I won't go into politics, the argument. And this is a Hebrew University. And if you want to visit, you're most welcome, Jason, and all the others. No, he is afraid. Okay, so we will all talk about spintronics and superconducting spintronics, but we have to remember what we want to do. We want to do, at the end, we want to have a logic devices, DRAM, SRAM, which are working with voltages, or flash memory, which is quite slow. We all want to have voltage memory devices working much faster. We want much less energy working with those energy devices. So we want a simple universal magnetic memory, maybe, which will be fast, dense, non-volatile, power efficient. So this is why we are talking about spintronics. But you have to remember that when we talk about spintronics and electronics have the same thermodynamic limit, which means we cannot have a memory or a bit which will not work at room temperature. Then energy for a bit will be smaller than the Fermi energy or the thermodynamic limit. But what electronics is about 4 orders of magnitude higher than the thermodynamic limit. In principle, spintronics, because we have less scattering and less heat, could work closer to the thermodynamic limit. So this is why we want spintronics, and at the end, this is why we want superconducting spintronics working even at higher frequencies. So we have to remember that when we start talking about spintronics. And of course, there are huge conferences about spintronics, and there are many spintronic devices. Even if I miss most of the talks going to travel around in Hawaii, there are huge conferences about spintronics. And you have to say that there are many, many kinds of spintronic devices. And most of you know most of them, so I won't go into spin transistor, spin, all the other things. But there are 2 major problems that we have in all the superconducting spintronics or in the spintronic devices, and I think we must address those issues very carefully. The first is a material problem. We are all a material conference, and I saw very nice talks of Maeda and Yossi, all talking about, and others, all talking about spintronics devices. But it's a very complicated material problem. It's not a simple silicon way of material problem. And the other thing when you think about spintronics, before going to superconducting spintronics, is you have a very low efficiency of spin separation. You need very high current to separate spins. So even if you can work on your spintronic device in very high frequencies, because you have less scattering, you still need a lot of current to separate the spins. So here you see anti go in one direction or the other. This is a non-efficient device. So I hope to convince you in this talk that we have found, together with our collaborators, a very simple way to do both spintronics devices and both to solve the material problem. We can work on silicon-based devices, very simple with silicon-based devices, and we can have an efficient way to have spin separation. And I will show you that this way maybe also have a simple way to generate superconducting spintronic devices in a much simpler system. So we start with a Chiral-induced spin selective effect. What is a Chiral-induced spin selective effect? And this is a work done in Weizmann Institute by our collaborator Rona Ahmad. What you see is that if you take chiral molecules which are helical, and you drive current through them, they act as a spin filter. So this is a very simple experiment. You take a double-strand DNA, you put a monolayer of double-strand DNA, then you put gold nanoparticle on top, and you measure the tunneling current from the bottom contact to the top AFM tip contact, or conductive AFM. And then you have a nickel layer, which is a ferromagnetic, and you can magnetize it either up or down, comparing on the magnetization. So if you magnetize up, you measure the current. You magnetize down, you measure the current. Then you can replace the nickel by gold, and you again measure the current. And you see something very interesting. You see that if you magnetize in one direction, you see high currents. If you magnetize in the opposite direction, you see low current. And if you use gold instead of nickel, you don't see differences between the magnetization. So this means that helical molecules, or molecules which are helical, this is double-strand DNA, act as a very efficient spin filters. And if you see the gap between those two spins, the gap could be going up to 1 electron volt. It's a huge gap. The molecule gap is 1 electron volt. You need to remember that when we talk about superconducting spintronics using chiral molecules. But the gap between spin up and spin down is about 1 electron volt. And this was confirmed also by a scattering experiment done in a science paper done in Germany by Helmut Zacharias. So we have a very large gap between the spin up and spin down molecules. What is the theory for this? This is quite controversial because many theories find this kind of differentiation between spin up and spin down going through helical molecules. No theory so far, or maybe there's no theory so far finds the right kind of gap. But if you think about it, you have a helical potential. And if you think about it, then the current maybe goes a tight binding potential through this helical potential. So you can think about classically as an effective magnetic field. But since the radius of those molecules are around 1 nanometer, the effective magnetic field could be huge. It's about thousands of Tesla. So you have a spin. One spin will have an effective magnetic field pointing in one direction. The opposite spin will have an effective magnetic field going in the down direction. And you will have a huge difference between the two kinds of spin. If you want to be more exact, you can have a Rashba-like term, which is called the V cross E term. And you can have a Rashba-like term, which goes due to the tight binding, or you have coherent effect, the wave function goes around, and you will have a spin splitting, and then again a spin gap going from as this spin goes up, the opposite spin will go down. There are also scattering models, which says, let's say that you have a helical shape, and let's say you throw a frisbee and it's spinning around, then you have a higher probability for the frisbee to scatter forward than if you spin it in the opposite direction if you have scattering backward. So if you have multiple scattering events, you will also have spin selectivity as our model like this. And right now we don't know, one of them will be coherent, one of them will be non-coherent. We don't know which model is right, and we are trying to do like people done here, a Aronoff-Bohm kind of experiment, or Josephson-like junction of experiment, to check if it's a coherent effect or non-coherent effect. If you want to take I've been many years in the army, in the infantry, so if you think about a bullet going through a gun, I don't know if you know, but the bullets are rotating around, and this is again preventing scattering to prevent it's going far. I don't know if you know that a bullet, if you shoot. I don't know if any of you shot a gun, but if you shoot a gun, the bullet is rotating, and this is again to prevent scattering. So you give the spin to prevent backward scattering. So no matter what the theory is, you have a gap, you're preventing backward scattering, and then you can do very simple spintronic devices, because all you need is take a metal, any metal, have those chiral molecules, drive current through them, and induce spin selective. It's also spin selective, and you can magnetize the substrate. Or you can do optically induced kind of you magnetize the substrate, or you can do optically induced, have an exciton, the exciton charge will oscillate, but one kind of charge will go down, spin will go down, the opposite will go the opposite direction. This effective, if the current goes in this direction, we have one kind of effective field. If the current goes in the other direction, we have the opposite kind of effective magnetic field, and we can magnetize the substrate. So overall, this is a very simple way to have spin magnetization. And we together, this is our paper, but also Ron Naaman wrote many papers, or Ron is also on some of those papers. We have many ways showing very simple spintronic devices using these schemes alone. So I will just show one of them. So this is a ferromagnetic nanoparticle grown by ETH, by Dorin Kamprimek. And then we use polyalanine, so it's covalently bound by the thiol bond to the gold, and by the carboxyl bond to the oxide of this ferromagnetic nanoparticle. And we can have a very simple, we need, it was published in high-ranking journals, so we need to have very nice pictures to convince the editor to pass it through. So this was a ferromagnetic nanoparticle, and I will show you that we have some kind of a Memristor-like behavior or hysteresis-like behavior when we start with high resistance, low resistance, and going back to high resistance. So this is, it was published in Advanced Material. The only, you just drive current through the high electron molecule. You magnetize the ferromagnetic nanoparticle either up or down. When it magnetizes in the direction of the majority, the resistance is high. When it magnetizes in the opposite direction, you inject the minority and the resistance is low. So here you change the you use polyalanine. So if it's left-handed, in one kind of magnetization direction. We can magnetize a ferromagnetic. We have high resistance or low resistance. With the opposite chirality, we can have the opposite high resistance or low resistance. And this is a very simple device. You don't need anything. You just take ferromagnetic nanoparticles, you just drive current, and you can see either high or low resistance. The only problem with those devices is that you cannot really erase it because the corrosive field here is very, very high. So we can only erase it with external magnetic field. But if you take lower corrosive field, you can even erase it, because if you drive voltages or drive currents that's above the band gap at 2 volts, you can erase this kind of device. So far I've convinced you, I hope, that there is a CISS effect. The CISS is a chiral-induced spin selective effect. You can take chiral molecules or even chiral oxide, drive currents through them, and they are spin selective. And you can do very simple devices out of them. This is silicon-based devices. So if I will talk about the 2 problems of spintronics, I think this may convince you that here the devices are very, very simple. We don't need nothing than the standard semiconductor technology. Actually, since we have several patents and we talk with companies, the only problem here is that the chiral molecules don't survive to high temperature, and silicon-based technology needs 500 degrees Celsius. So this is the main problem going back to technology, but it's more advanced than, I will say, superconducting spintronics so far. So what can I say about, so I didn't show you that we need low current, but I hope to convince you that those are chiral effects in Israel. What can you say about the CISS? What happened in equilibrium? So this is a very simple experiment we did. We took, here I want to convince you that we need actually no current or very small current to have this kind of effect. So those are samples grown by Stewart-Perkins groups and IBM. It's a cobalt, ferromagnetic cobalt, 1.5 or 2 nanometer thickness covered with gold, very thin gold. And what we did is selective absorb of the chiral molecule. So this is a Stewart-Perkins sample, the cobalt. So the easy axis is perpendicular to the surface. Then we add the chiral molecules. And here you see the chiral molecules sitting above this ferromagnetic material. So here we have chiral molecules. This is D-wave, D-polyalanine, and here we don't have. And we can do it in smaller and smaller domains. So we can take an AFM and measure the topography and measure the left-handed, or this is the right-handed actually, because chirality in chemistry is very confusing. But this is a right-handed molecule, this is a left-handed molecule, because there are several names for chirality and there are several definitions of chirality in chemistry. And we can take an MFM tip and measure the magnetization. So you see here, this is equilibrium. We drive no current, we put no light, nothing, but we see the magnetization. So if one kind of molecules magnetize in the up direction, the opposite kind of molecules magnetize in the down direction. So this is quite surprising, and it was published just recently. And if you think about it, we don't have a real theory for this, because we can say that the molecule is a dipole, and of course the dipole, if it's a dipole, charges will go to one side or the other, but then we'll have, if we have charge separation, we'll have spin separation, because the molecule acts as a spin filter. But this is not enough, because first of all, if in equilibrium, then after some time the other spin will arrive. And even though if you think about, even this is very, very small, because we have very low, we have 10 to the 13 molecules per centimeter square. It's 12 orders of magnitude lower than what you would think about spin torque transfer or magnetizing a ferromagnetic surface. You can talk about wave functions that we hear. We hear the wave function penetrates more because of the helical shape. The spin is penetrating more than the other. So those are all hand-waving arguments. But the bottom line is that here we didn't pass current. If you calculate the number of molecules and you think that one electron went through the molecule to the surface state or something on the surface, which means that one spin per molecule, we are 12 orders of magnitude with what we expect with spin torque transfer. So either it's a very efficient device, or we don't really understand what's going on. So it's very simple and it's very, very efficient. You can think, yes, sorry.
The role of the gold layer you had was for the good interface, or?
The gold layer had two kind of, the role was twice. First of all, we didn't want the cobalt to oxide because we put it in a solution. It's where it's self-assembly. And the second thing is we use thiol links and thiol covalently bond to gold and not to the cobalt. But it's a very thin gold layer. And actually, gold with chiral molecules become paramagnetic because it's enhancing. If you take a paramagnetic also with chiral molecules, you're enhancing the magnetization, the surface magnetization using chiral molecules. So it really helps. Yeah.
So is there enough signal here to put these in a split diamond
Yeah, yeah.
Is it just shifted? Is this like
It's shifted, yeah, it is shifted. In the paper, the referee asked, we did both squid, Hall measurement, and MFM. It's exactly it's exchange bias. So you can see maybe the answer is that the charge oscillates, and if charge oscillates, it acts like a spin pump, because one kind of spin goes to one direction, the opposite going in the other direction. So you just, the charge stays, but you pump spin from the surface. So maybe this could account, if you calculate the frequency of this, you can expect this could account for the missing orders of charges. But it's a very strange phenomenon. So since we are in a superconducting conference, but actually we did it before, we asked ourselves, can we use superconductors to check what's happening here? Because the superconducting surface will be very sensitive to those kind of chiral molecules. And maybe we can see a full coherent effect checking the superconductivity. So I know that most of you don't know how STM works. I skip this slide. So what we did is put chiral molecule on the simple S-wave niobium surface. And with Oded Milo, our collaborator, which should have been here but actually couldn't come because of personal reasons, we measure the density of states on the niobium surface with and without the chiral molecules. So this is what we saw. We have selective absorbance, so we don't have chiral molecule. We see the standard superconducting gap. In Oded STM, we cannot go below 4.2 Kelvin, and we cannot put so far magnetic field. But we can measure this kind of a gap. And when we put the chiral molecule, so this is a molecule-free region. When we put the chiral molecule, we started to see very interesting density of states, which are always symmetric. So I don't think it's a Shiba state, but we couldn't go to low enough temperature. And those states are not just, it's not just that we are not in the tunneling regime. We really see a zero bias conductant peak. It's symmetric around the gap. And those states are really, really strange. So it's not Shiba states, so we could fit those kind of states if we want them to P wave plus S wave according to a kind of model. And we think we have some kind of, the chiral molecule induce a mixing of P wave or D wave plus an S wave, and the fit was quite good. But notice also that the ratio between the P wave and the D wave is about 4 to 1 or 3 to 1. This is exactly the ratio which we measure in spin selectivity if we put it on a device. If you don't, I didn't show you, but the up current is higher than the low current, but about the same factor 3 to 1. So maybe this hints that we do have a P-wave kind of superconductivity. I know that it could be magnetic impurities, but even this is very interesting because this is not a magnetized molecule, because it could have spin selectivity or act as a spin pump, but there's no magnetic atom here. So even if it's a Shiba state, which I don't think so, it's quite interesting. So this was published in New Journal of Physics. Of course, you know, we argued with PRL a lot, but it's a New Journal of Physics, which we are happy. But we wanted to see if it's true. Oh, those are all the reference. All this effect disappear, of course, above TC. And if we take just the surface treatment, we don't see this effect. If we take non-chiral molecules, it's not the molecular effect. We don't see this kind of effect. So maybe, so far, that we can change the surface of a superconductor in a very simple way from a standard S wave to a kind of a P wave or a D wave superconductivity just by putting the chiral molecule. If this is true, of course, then we can go mimic all the work about superconducting spintronics in a much simpler system. Like Dirk asked, find me a simpler system. Maybe this is the simpler system. So what we want to do, and I know there are many more for the crowd that did superconducting spintronics, what we want to do is to do simple superconducting spintronics. So the device we used is the first time was a very simple device. Or actually, it wasn't as simple as we thought it would. It's just a niobium surface, chiral molecules, a polyalanine, the standard polyalanine. We put a graphene flake. It's a thick graphene flake. So it's not a graphite. It's not a one-layer flake, graphene. It's just a thick layer because we didn't want to put tunnel barrier. Usually in our devices, we put oxide here, but oxide will ruin as a coherent effect or may ruin the coherent effect. So we want to have a contact, a good contact for the chiral molecules, which will not ruin, which will not have scattering of spins. And we put a gold contact on top. And we measure the density of states. Here we can put, of course, magnetic field. Here we can go to lower temperature because this is done on a device at our laboratory. going down to 1.5 Kelvin. And you see a very strange density of states, really close to what Yossi showed us. It's much wider. I will tell you in a moment wider, but this is more or less what we, after calibration, this is more or less the gap. It's a lot of the voltage is falling on the junction of the graphene and gold junction. And we see two kind of peaks, and it reminds us maybe a P-wave superconductor or the chiral P-wave that we saw before. Just checking that the shape is related on the gold contact. When we go to a 3-probe terminal, we could go to the right band gap. So it's wider mainly because a lot of the voltage is not falling on the junction. So if we could try to do a theoretical fit, we could, of course, then it's becoming a problem because maybe the graphene is have a proximity, so we have a 2-gap problem. So if you take a low Z and a 2-gap model, we can fit to those kind of, we don't think that this is what's happening, but we could do a right fit. Okay, we can take a high Z and a P-wave model, and we can also have those kind of fit to those kind of spectra. So we don't know exactly which one of them are right, but we are going to those, this is what I wanted to ask you, we are going to those theoretical paper of Yossi and Kashiwaya, yeah. And they claim that if you see this kind of spectrum, of course, the width is on the strontium rubidium oxide that we had several talks before. Then below HC2, if you have a chiral P wave, below HC1, you should have the peak, or the peak should change monotonically because you break the symmetry of the chiral P wave. So we try to do this kind of experiment on the peak, and exactly this is what's happening on this kind of peak. If you change the magnetic field below HC1, it's hard to see here, the peak doesn't matter if you go a negative field or positive field, you always have this monotonic kind of behavior. And if we change to non-chiral molecule, we saw non-monotonic behavior. If we change to other kind of molecule, we saw only the monotonic behavior of changing of the peak using those kind of chiral molecule. So maybe this is another hint that we have a P-wave superconductor on just by putting chiral molecules on top of a standard S-wave superconductor. Of course, we'll now need to build a 2-terminal device, try to do a lateral superconducting spintronics using this effect. But this may hint that indeed we may have superconducting or some way to have a kind of superconducting spintronics using this kind of chiral molecule. So what do we see? We see a strong collective effect. We see a strong effect using those chiral molecules, even in equilibrium. I think we can say we can solve in standard spintronics both the current problem because we don't need high current, and we use very simple materials. So it's both the material problem as the current problem. We see superconducting. It may be good for superconducting spintronics. Actually, we now see, and this is a paper that is just submitted, we can see the opposite effect. I told you that this is not related to superconducting, but I told you that if we put a ferromagnetic substrate, we put chiral molecules on top, we can magnetize the substrate. We can now take a substrate, magnetize the substrate, and this distinguishes between the two chirality of molecules. Why it is important? Not for Spintronics devices, but the pharmacy market really need to separate two kinds of chirality because most of the drug, nature is mainly chiral. This is probably you know, and actually we think that the CISS effect is the why nature chiral. We would just receive a grant trying to explain why nature preserves chirality. But also the drug we use are mainly chiral. I don't know if you know the story about the 60s. That, what was the name of the drug was? What? Thalidomide, yeah, exactly, which the chirality breaks, and then a lot of the children or women who use this drug while pregnant, the children were born with no hand or legs. And so chirality is very important in nature. We think because about spin, and we show that just by magnetizing the substrate, we can have high absorption or low absorption depending on the chirality. So this is also important for other kind of application. So in summarize, we think we can do very simple spintronics and superconducting spintronics at low current. So thank you very much.